So next, we should talk about the integration of a scalar function along a curve. And here we need to begin our conversation about orientation of a curve. So as I think about a set of points which forms a curve, you may or may not want to think about giving it a direction. Certainly a path has a direction, right? But just to start with, you could think about just the set of points being a curve, right? But it wouldn't have a sense of direction. But once you think about it having a direction, then it's called an oriented curve. So this C I'm talking about here is an oriented curve. It has a sense of direction. So minus C would mean the same set of points, but in the opposite direction, which is hard to draw in the same set of points. But so you can understand this picture for what it means. Same set of points, right? Same set of points, but the opposite direction. Okay. And so if you have a curve and if you have a path and you want to just reverse the direction of it, you could call that the reversal of the path. And I have some formulas here for doing that to a line segment. So like I have a line segment with parametric equations as given here, and that gives me a path that goes from 1, 2, 3 to 5, 5, 5. If I want minus L, then that's a path from 5, 5, 5 to 1, 2, 3, and I say we can parameterize that by this. And I point out that the reverse path switches 0 with 1 and switches 1 with 0. So in this context, the reverse path is given by the initial path evaluated at 1 minus t. So anyway, we can reverse a curve, right? That's one thing we can do. Here's another example. I have a circle from pi to 2 pi. So let's see here. For pi to 2 pi would be like this. It's like that, right? Make sure I'm in frame here. Pi to 2 pi, that's C. And then I say, well, you could if you want to parameterize minus C, which would be what? Like same set of points, but instead of going counterclockwise, we go clockwise. Right? Sorry, I'm trying to draw the same set of points. I failed, but imagine it's the same set of points. And so I say we could use beta of t as gamma of 3 pi minus t. That would work. And what's my again for pi to 2 pi? Let me see, is that right? Beta of pi, what's that? So I think there's a couple different things you could do here. Some of these, sometimes I'm making the same domain for the curve and its reversal. But if you read my definition of reparameterization down here, I'm not assuming that they have to share the same domain. So I think there's a couple different ways you could go here, and I think I have dabbled a little bit in both worlds is a way to put it kindly. Beta of pi, 3 pi, well, that would give me gamma of 2 pi, right? Which by construction is, well, that point, 1, 0. And beta of 2 pi would actually be gamma of pi, which would be minus 1, 0. So yeah, I think this formula works to give the red path going from 1, 0 to minus 1, 0. And this minus t on cosine and sine, that kind of formula, does give a clockwise rotation to the circle. So okay, I'll believe it. But what I'm trying to say here, guys, is just that you could do it a different way. Okay, you could do it a different way. But what I showed in the example is one way you could do it. There are others. Now here I define what's called a reparameterization. Oh, that's a mouthful. So if you have a path from A1, B1 to R3, and another path from A2, B2 to R3, then the second one is a reparameterization of the first one. If you can find a bijective, hey, you guys know what that means, woohoo! One-to-one and onto, continuous function. I guess we don't know what continuous means yet in analysis, but oh well, all in good time. But you know what continuous means in calculus terms. It means that the limits match the values of the function, right? It doesn't jump around, right? Anyway, so this parameterization goes from A1, B1. Basically, the parameterization takes the domain of gamma 1 and gives you back the domain of gamma 2. And it has continuous inverse. So I can also go from the domain 2 back to domain 1. And it relates the two paths according to this relation right here, right? So if I plug in, I'll try it again here. So it says gamma 1 of time t is also given by gamma 2 evaluated at u of t. So they're connected in this way. We looked at this idea already when we looked at the reparameterization with respect to arc length. This is just generalizing that. So there are two different possibilities. If you're going to have a continuous inverse, either u needs to be increasing, or it needs to be decreasing. If it wasn't strictly increasing or strictly if it wasn't increasing or decreasing, you wouldn't be able to find an inverse because you wouldn't be one-to-one. If you go up and then you go back down again, all right, you would fail the horizontal line test is what it boils down to. So you need to have either that the derivative of the reparameterization is everywhere positive or it's everywhere negative. If the reparameterization is everywhere positive, that means that the path and its reparameterization are consistently oriented. On the other hand, if the reparameterization is negative, that means that they're oppositely oriented. So like a reversal of a path could be a reparameterization, possibly. Although I think technically, well, I guess, yeah, it's fine. Never mind. I just, it just so happens that I have, in my example before, I have both of these intervals being the same. Like example 2.4.2, both the initial, the first and the second. If you think about gamma being gamma 1 and beta being gamma 2, I think that's an example of reparameterization actually, where A1, B1 is pi to 2 pi and A2, B2 is pi to 2 pi, and explicitly u of t in that example is what? 3 pi minus t. Right, and so du dt is minus 1, which goes to show you that c versus minus c, c versus minus c are oppositely oriented. So I do think this language makes sense, but anyway. So I'm sorry this is taking some time. It always takes a little bit of time for me to try to unwind these ideas. The basic issue here, guys, is that there are many, many different paths to cover one curve. So we have to address this ambiguity when we're setting up calculus, because the calculus we're going to do uses a parameterization to set up an integral. But the thing is, that integral should be describing something that's intrinsic, that's independent of our choice of parameterization. So that's why this discussion is needed. But anyway, so just to relate, if we have this path and we have a reparameterization, their velocities are related according to the chain rule like this, right? So, okay, now that we've got all that, I can define the line integral of a scalar function with respect to arc length. The line integral, so let me try to draw a picture of this. let me draw a picture of what we're integrating. So it's something like this. You've got, I can only do it two-dimensionally, but if this is the curve, right, and then we're thinking about, I don't know, like maybe there's a curtain over the curve, all right, and that curtain, it's taller some places, it's shorter some other places. Right, 0 there, and it comes back up here, whatever. So this is the curtain over the curve C. I'm going to say that f of r of t, that's the height of curtain, height of curtain at r of t. Now r of t would be like a point on the curve. So if I want to calculate the area of such a curtain, right, as in if I was to take that and just lie it flat and calculate its area in the conventional sense, what I need to do is basically think about chopping this curtain up into like little things like this, right? And if I was to take that and blow it up, it would have, basically the bottom would have length ds, and it would have height essentially f of r of t, whatever that was there, right? So that's the width, that's the height. So the little bit of area from that would be f of r of t times ds. But we know how to calculate arc length in terms of speed, right? So that's f of r of t ds dt, and so I integrate this. Integrate over time, and that will calculate the area of such a curtain. That's the problem that motivates this integral, essentially. All right, but the same setup would just as well, if instead of being height of a curtain, if it was like mass per unit length of a wire, then this integration we're about to do would describe the net mass of the wire. Or if it was charge per unit length of a wire, we could be calculating net charge. So the area of that curtain and the mass of the wire, the charge of the wire, none of these should have anything whatsoever to do with our choice of how we parameterize C. Right? The parameterization should just be a convenience of calculation. Let's see here. So I think the definition I have carefully stated. Next, here it is. Yep. So there's my definition of the scalar line integral of f along a curve. To integrate, what we do is we pick any parameterization of the curve in question that you like. All right. I think it has to be a reasonable parameterization, like a differentiable parameterization, okay, in order to make sense of this calculation. But let's say choose a differentiable path that parameterizes the curve, and we also need that the function is defined along the curve. All right. Then the scalar line integral of f along C is given by, we take the function, we evaluate it, the parameterization, and then we multiply by the speed and multiply by t. Because remember that this is like that mnemonic I was talking about before. We're really like f at the point, right? And then this, I'm just going to say of the stuff. Let me not write it out again. But that is ds dt, right? And that's dt. So like you think about the dt's canceling and giving you back s in some sense. That for me is a guide of how I set up this integration and partly of like intuition why it's reasonable. Now, for this integral though, to be careful, a proof should be given that shows that this integral is independent of our choice of parameterization. And that's what the next half page or page or so is about. So what I do is I say, okay, well suppose you had two parameterizations. I want to show it doesn't matter that which one we use. It's going to be the same calculus. And so here's the setup for gamma of 1. I switch it over to gamma 2. Out pops by the chain rule this du dt term. And then there's two cases to think about. Either it's orientation preserving, in which case the du dt is positive, so just the absolute value is the quantity again. And so we can do that integral is that. And then the cool thing is that this is by u substitution the setup of the integral in the other path. So in other words, I've just shown that you could calculate with gamma 1 or you could calculate with gamma 2 in the case that the curve has been, in the case that gamma 1 and gamma 2 are orientation preserving, we get the same answer. It doesn't matter what choice of parameterization you make. On the other hand, if you were to reverse the curve, if you were to look at a, rather, if you're looking at a reparameterization which had disoriented the curve and replaced c with minus c, then when you go to that absolute value, you pull out a minus, right? And so that will flip flips the bounds, I think, here. Let's see here. So the minus, because that's negative. So u of a1 is b2, and u of b1 is a2. U of a1 is b2. U of b1 is a2. Because they flip the bounds. And so when I make the u substitution, I should, that means a1 goes to b2, and b1 goes to a2 like I have. That's good. And then to get from here to here, I flip the bounds again. And that's what I need to do in order to get back to how we set up the integral with respect to path 2 by the definition. So yet again, it shows that it doesn't matter which path you use, whether it's the path or an oppositely oriented path, parameterizing the same curve, we get the same answer. And that also shows, by the way, that the integral of FDS over the curve C is the same as the integral of FDS over minus C, which is what I've argued must be the case, but we've also proved that this is in fact true. Later, we'll look at something called a line integral of a vector field, and I'll just write it now because, you know, we'll be to it before you know it. But later, we'll talk about FDR, this being the line integral of a vector field, which will calculate the work done by the vector field along the path. And we'll see there that it's not quite so easy. There, the integral along the opposite direction of the curve actually gives us minus the other one. So that's basically saying if the work done along the curve C is 10, then the work done along the opposite direction of the path would be minus 10, because this calculates work done later. But anyway, yeah. So here's an explicit formula for how we actually would calculate it for a specific one. If you happen to have like parametric equations for the curve, then you calculate f of, you know, x, y, z, evaluated the parametric equations, and then the square root of x dot squared plus y dot squared plus z dot squared. That's how we actually calculate. Here's an honest to goodness example with formulas in it. So suppose you got a helix, x equals r cosine theta, y equals r sine t, z equals to t, and I give us that the mass per, let's see here, I said that the linear mass density is, oh, this is a typo, folks. I'm sorry about that. I meant to say dm ds, the mass per unit arc length, is given by z, which means that dm is z ds, right? So the total mass, to get the total mass, I integrate, you know, mass total equals the integral of dm, right, along the curve. I mean, this is a new, but what that means actually is we integrate z ds over the curve. And what's that look like? Well, z times this is the speed times dt, right? But the speed of this is square root of r squared plus 1, we calculate. We, in a previous lecture, had r squared plus m squared. This has m equal to 1, so it's r squared plus 1. Z I don't expect you to memorize that, by the way. I just happened to do it recently, so I remember. Z equals to t, that puts that t there. And so when we integrate this, it's a t times the number, which gives me t squared over 2 times that number, evaluated from 0 to pi, 4 pi, because the problem said, that was given in the problem, to look at the helix for basically 2 rotations. And the total mass I calculate is 8 pi squared times the square root of r squared plus 1. Of course, we can also calculate the arc length, and we would get 4 pi times the square root of r squared plus 1, just the same. Because to calculate arc length, we just integrate speed. See, this is something new. We're integrating a function times speed to calculate the net amount of something distributed along a curve. Another thing I should define, because it's fun, is the average of a value along a curve. So if I want to talk about the average of f over the curve, I divide like 1 over the length of the curve times the integral of f along the curve. So like for example, in the previous example, we could figure out what's the average mass per unit length on that, and so 1 over L times the integral of f ds, we just worked that out, was 4 pi square root of r squared plus 1. The arc length was 4 pi square root of r squared plus 1, so those cancel, and we get that the average mass per unit length was 2 pi. So I say that that's not particularly surprising, since we had well, anyway, I say it. I mean, I could add words here, it wouldn't help. Now, more generally, you may recall from calculus, we sometimes like to calculate the centroid of something, right? Like the middle of it. And so if you want to calculate the centroid of a curve, you can do it. You just integrate x. So here delta is dm ds. So delta is the mass per unit arc length. So integrate mass per unit arc length times x with respect to arc length, or y with respect to the density, or z with respect to the density. And these give us the coordinates x bar, y bar, z bar of something called the centroid, or center of mass. The centroid is a geometric thing for a curve. It just assumes that the delta is 1, technically, right? So, I mean, and here I actually calculate the centroid for the helix, and I find out that the helix has a centroid which is 0, 2 pi over r h. Let me try to foolishly draw the helix that we're looking at. This one I did for this helix. I just went. Is this a helix actually? Nope, this is not a helix. This is a circle on the plane z equals to h, because there's no. So like here's z equals to h. This is a circle, and I found that 0, 2, so the sorry guys. Zero, 2. I just don't believe that. The centroid of that circle should be this point right here, and that point is 0, 0, h. So I'm happy that x bar worked out to 0. I'm mystified that y bar worked out to 0. It just feels wrong. Y is ds is r dt. Y is r sine t, so I get that. I mean, the integral from 0 to pi for sine, it is 2. I'm sorry. I'm sorry. I am currently stumped by this. Why do I want to say that the circle has centroid right there in the middle? Why am I getting... Oh, I know why. Is this a circle? I'm sorry, guys. I'll get it eventually. Is this a circle? No, it is not a circle, because we don't let t range over 0 to 2 pi. T goes from 0 over to pi. So it's that part of the circle, right? So it makes total sense that the x bar, the average x should be 0, right? But y, it should be to the right, right? So the centroid is actually like over here, which makes total sense. Because, again, it's not a whole circle, so like the average location of these points is like right there, which is 0, 2r over pi, comma h. So anyway, that's a brief introduction to integral of a function along arc length. You can see that this is something we can definitely pretty easily do once we know about how to parameterize a curve and how to calculate speed. And so it's a natural topic to include here. Not everybody includes this topic here, and I don't test on this too deeply. Like there might be just like one problem or something. I'm mostly trying to get us starting to think about how we integrate along a curve and how parameterization plays a role in that. So we'll come back to integration much more deeply as the course progresses. So I'll stop here for now. I think that's it for the material which is on your test 1. So of course, bring me your questions, and thank you.